Hello everyone. Today we are going to focus on numerical solution of ordinary differential equations or ODEs. Now there are so many different algorithms for this topic in the literature. We are going to focus on two of them today. The first one, which is kind of like the simplest one to understand and implement, called the Euler's method. And then another one that is commonly used in many other methods where they need to solve an ODE numerically, including MATLAB, and that method is called Runge-Kutta. Now, Runge-Kutta has different variations. It's not just one Runge-Kutta. There are so many different Runge-Kuttas in the literature. With the one that I'm going to focus on is called the fourth order. But before we do any of that, the first question that might come to your mind is, well, why should we solve ODEs numerically in the first place? Why can't we just analytically solve them and come up with a function instead of a bunch of points which have their own advantages? So let's talk about why we need to do ODEs, sometimes solve ODEs numerically, and what are the advantages and disadvantages, very briefly, and then we talk about these two algorithms. So why do we need to solve some ODEs numerically? The answer is, well, the reason is many of the ODEs that exist in the literature, in the nature, and so on, you cannot solve them analytically. Our math is not there yet. We cannot solve them. And you might say, really? Yes. For example, one of the simplest problems that you probably are familiar with is the pendulum. So if you have a pendulum with length L and mass M, discrete mass M at the end and length L, and the deviation angle from the vertical direction measured in counterclockwise manner here is theta, there is no torque here at the pivot and no friction, then you can easily show that the governing equation of motion for this degree of freedom theta, it is going to be theta double dot, or alpha basically, is equal to negative g over L sine of theta. Clearly, it's a second order differential equation. It is nonlinear because the dependent variable theta has a nonlinear function of it here, sine. And if I give you two initial conditions, right, it's second order, you need two initial conditions. Let's say theta at time 0 is what? Let's say 60 degrees, pi over 3, and you release it from rest, so theta dot at time 0 is 0. Don't forget the units. And my question is, could you solve this for me and give me theta as a function of time? And can you do that? And well, as it turned out, you cannot. The ODE looks very simple. This is a constant number. There is no other term. It's just sine of theta. That's all it is. And there is no analytic solution for theta of t which has a finite number of terms. So the solution for it is going to be an infinite series in terms of t, and you can never keep adding stuff together forever. So at some point you have to truncate the series, and that's where you start getting errors. Okay, so it's going to be approximate. It's not going to be accurate. And as I said, you cannot really come up with a closed form solution that has finite number of terms. Actually, mathematically, it is shown that it's impossible using the math functions that we know. Okay, why? Because I don't want to get into details of that, but it leads to calculating something called second elliptic integral that so far we have not been able to solve. Okay, and the second elliptic integral, you can take more look into that. That's an interesting integral that nobody has solved analytically so far. There are only infinite series for it and numerical approximations. And you might say, well, what does it have to do with elliptical? Well, you can go look it up, but another interesting thing before I move into numerical solution is, well, if we have an ellipse and the semi-major and semi-minor axes of this ellipse are A and B. So A is half of basically semi-major and B is half of semi-minor diagonals or axes. If I ask you what is the circumference of this ellipse, not area, circumference, what is L, the circumference, as a function of A and B? Okay, what is it? Could you give me a definite function with a finite number of terms that can accurately calculate the circumference of an ellipse? Well, you cannot. And that's another thing that you might be wondering, well, we have been to the moon, we are trying to go to the Mars. Can't we just come up with a formula for the circumference of an ellipse if you have A and B? No. The only solution is an infinite series, okay? And there are very good approximations, but there is no accurate closed form with finite number of terms formula for it. And these two guys are quite related to each other. Both of them are related to that second elliptic integral. So yes, there are some ODEs that you cannot solve their governing, there are some systems that you cannot solve their governing ODEs. And they are mostly nonlinear systems, okay? And my students sometimes ask me, well, we say that we can solve linear systems, ODEs of linear systems entirely, or at least to a good extent. What about nonlinear systems? What percentage of the systems in the nature are linear? What percentage of the systems in the nature are nonlinear? So they want to know the importance of this numerical solution. So are we trying to find an algorithm or describe algorithms for numerical solution, but those ODEs that are nonlinear are only a small percentage of all ODEs that we know and we have derived? So then it's not a huge deal. But if most of the ODEs we know in the nature are nonlinear, then, and we cannot solve most of them, then this numerical solution thing is a big deal. So they always ask me, and the answer is, guess what? How many of the systems in the nature are linear? How many are nonlinear? Well, it turns out that all of the systems in the nature are nonlinear. Okay, we linearize them when we try to come up with a solution, approximate solution for them, right? Like this pendulum. Clearly the system is nonlinear, but probably if you studied basic vibrations, or you will study basic vibrations, one of the things they say is, they say this theta, okay, this theta max, the maximum angle that the pendulum will go through, which typically is equal to this initial condition, this, we're going to limit it to a small angle. So for example, we say this is less than or equal 6 degrees, small angle. And if that's the case, then I can say that that term sine theta that appears in my ODE can be approximated by the theta itself. So now your ODE becomes theta double dot equals negative G over L times theta, which is now second order linear. And now if the system is linearized like this, you can show that your theta of t is going to be a harmonic function like this, where A and B are determined by the initial conditions, and this omega here is the square root of G over L, which is this coefficient. Okay, but if the system, we consider it the way it is and we don't impose limitations on it, these systems are nonlinear and we cannot come up with a closed form solution with a finite number of terms. So we have to solve this numerically. Now, what does numerical solution mean? So in numerical solution, when I give you this ODE again, this guy, instead of coming up with a function, theta as a function of t, you are not going to come up with a function. You cannot do that. Instead, you will have a bunch of points. So if this is theta and this is t, you start from initial condition and then you come up with an update or a recursive equation or equations which based on the value of the previous iteration and the forcing function, we'll talk about forcing function or functions, then you can what? You can basically come up with the value of the function theta at the next time point, and then the next time point, and the next time point, and you keep what? Getting basically a bunch of points, not a real underlying function. And then if you want in the software, well, you can connect them by lines or any other function and come up with something that looks like a function, but it is not really. It's just a bunch of points connected together. Okay, so this is a numerical solution, and again, it does not give you a function. So, for example, one of the terms that we have, and it's important to learn it right now, is this distance between each point and the next point on the x-axis. So if you project them on the x-axis, this distance from one point to the next, we call it the step size. Okay, and we show it with h or delta t, whatever you want to show it. Okay, so we call it the step size, and in the algorithms that we're gonna look at today, we consider this guy to be constant, but there are many other ways to make this h variable based on how fast the function is changing. And if you use the command OD45 in MATLAB, which is used for numerically solving first order ODEs, you see it typically uses basically a variable step size unless you ask it to do fix a step size. So we have this step size, and clearly the smaller the step size, the more number of points we are going to get, and we're going to get a better approximation of the actual underlying function that we don't know. And sometimes if you make this h big enough, your solution is going to go completely wrong, your approximation, because numerical solution is an approximation, okay, of the actual function. It is going to be what? It is not going to be any close to the underlying function, and it might actually get further and further away, and we say the algorithm is diverging instead of converging. Okay, so this h, you have to make sure it's small enough. That's one of the things we talked about. And now the other thing is, now what could be a disadvantage of this method? First of all, I don't have a function here. So for example, if I want to know the value of this function at this time point t, which is between this sample point, so I want to know at this time t, what is the value of the underlying function? Well, for that time t, I do not have a sample. I have a sample to the left and the right of it, but nothing exactly there. So what I need to do here is, using these 2 points that I found by my numerical solution and the location of this point with respect to the left and right, I need to do what we call interpolation. And that's one of the topics of one of our future lectures, okay, how to do interpolation and approximate this middle point. Sometimes the t that you have is outside the range of time over which you solve the ODE. So you typically start with some initial time and keep going and solving until what? Some final time, and then you stop. You cannot keep going forever. Okay, so you have to stop at some point. And now, if you ever want to find the value of the function outside this range ti to tf, let's say somewhere here, then the best thing you can do is trying to basically predict, if you extended this guy, if you don't want to resolve the ODE from ti to this new t final, then you try to use the closest values of the function to this endpoint and try to basically from these points or these last few points try to what we call extrapolate how the function would have behaved if I continue the simulation and then what? Come up with the value at this unknown point. So we call it what? We call it extrapolation. And again, we're going to talk about these topics in the future, but as you know, again, since I have only a fixed number of points, if I want the value of the function at any point other than this sample point, I have to do interpolation or extrapolation, okay? I cannot just plug into a function, correct? When I had the function, when I could analytically solve, all I needed was, if I had this function, I plug the value of t at anywhere I wanted into the function, it gives me a number. So you see why analytic solution is preferred, right? You can evaluate it at any point that you desire, and it's going to be accurate. But here, you're just doing approximation. And when you solve ODE, you have approximation. When you do interpolation or extrapolation, now you have even more approximation. So the numbers that you get here and here are even less accurate than the numbers you got during solving the ODE. So you have accumulated error, basically. So that's one disadvantage of numerical solutions. The other disadvantage is if you get a function like this, you can see the effect of the parameters, okay? So for example, you can see how changing the length of the pendulum would change the behavior of theta, right? You see, for example, if you choose a longer pendulum, it means the frequency of vibration is going to go down. So the longer the pendulum, the slower the oscillation. The shorter the pendulum, the faster the oscillations. Okay, so you can see the effect of parameters that are involved in modeling your system directly onto the degrees of freedom or outputs. While here, they are hidden, they are not directly shown. In the value of each one of these points, you are not going to see L directly. Okay? So it's always a good idea that you can keep it as a parameter, but it's not going to be as obvious as this one. So the effect, if you want to really see the effect of parameters and how you can change some parameters to achieve something that you desire, is always the analytic solution that is preferred over numerical solution. Not that here it's impossible to see the effect of L. You can still do something about it, and we'll talk about it, but it's not as obvious as this. And finally, the other thing about analytical solution, as I said, is whether they would converge to the actual solution, or the difference between them and the actual solution is limited, reasonable, or it's getting bigger and we say the algorithm diverges. So we have stability and convergence and a bunch of other issues that we have with numerical solution. And that's a topic of its own. If you have time, we'll talk about it later. But just keep in mind that just if you find a recursive equation and keep updating and finding a bunch of new points, it doesn't mean necessarily the numbers that you got are accurate and meaningful. Okay, you have to make sure the stability and convergence of the algorithm and the amount of error that exists. Okay, that these are important things. And as much as time allows, I'll talk about a little bit of them. So you see, numerical solution has some disadvantages, clearly. But, well, when we have no other way to get around it, when we cannot solve analytically, well, the only thing we can do is to go numerically. That's the best tool we have. So hopefully by this point you understand why numerical solutions are important, because they are the only tools we have. Fine. Now that we got all this, now how do we do a numerical solution? The first method in the literature, as I said, one of the simplest, is called the Euler's method. And this method is simply based on discretizing the derivative and approximating it, and then coming up with an update equation. Okay? Now, note that this method is good for solving what? First order ODEs. if you want to solve second or higher order ODEs, you have to break them down into first orders. How? I'll show you. But this Euler method and the next method, Runge-Kutta fourth order, we are talking right now about how to apply them to first order ODEs. For higher order, I'll tell you what you have to do. So so for example, right now, this is a second order ODE, so I'm not going to apply Euler method directly right now. But what I will do is, I assume my ODE is something like this. Like x dot, correct, is equal to a function of x and t. Okay, like for example, something like what? X cubed, and then minus cosine of x squared, and then plus t times exponential of negative x, and plus 5. So if t is explicitly there or t is not explicitly there, it makes solving ODE analytically a little bit different, right? You know, if t is there, so the equation is time dependent, solving ODEs analytically is a little bit harder compared to when these coefficients are constant. But here, for numerical solution, it does not really care how complicated this forcing function is. By the way, when I say forcing function, I mean this right-hand side of the derivative, okay? The function that is making this derivative change and so make x change versus time. Okay, so this guy is what I mean by forcing function. So again, for numerical methods, the complexity of this right-hand side is not a big deal, unlike analytic methods. So now I say, well, this x dot here, the definition of it is what? It's the limit of delta x over delta t when delta t is going to 0, right? And you cannot really plug in 0, but it means as you are calculating this ratio and making delta t smaller, 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 we see where this number is heading, okay, where it is converging to, and we call it the limit. So here I do an approximation and I say, well, I'm not going to choose 0 because I cannot divide by 0, but I'm going to choose a small number for delta t myself, and I will say this is approximated by the ratio. This limit is approximated by the ratio when this delta t is what? Small enough. When we say it's much less than 1, it means it is quite small. Like what? Well, here is the topic that we have to talk about, the step size. But let's say, for example, for now, let's say this is like 10 to the negative 3. Okay, so we say the limit is equal to the function itself when delta t is small. And here we are assuming the continuity of the solution. So, for example, if I have, let's say this is my solution, x versus time, and it looks something like this. Well, if I want to look at, or let's say this is x dot versus t. If I want to look at this x dot versus t or x versus t as t goes to somewhere, right, or delta x over delta t, then instead of looking at 0, I can approximate the value at 0 where? Very close to it, correct? So if this limit is 2, let's say, if I zoom into this area and come up with some point here at a small t, if I read the value here, which is evaluated at a small t, this might be like 2.005 or something like that. So I can say these two numbers are what? approximately equal. Okay, so at a small number I read it instead of going all the way to 0. Okay, and clearly this approximation is good when I'm close enough to 0, which means when this step size delta t, which as I said in your algorithms we call this h instead. This is small enough. And so delta x means what? Means x at the new value minus x at the previous value divided by delta t, or x at the new value minus or x at the current minus previous divided by delta t, depending on which side you are taking, right? Because this derivative, it has a right derivative and a left derivative. So here, if I use the definition of right derivative for it, this is going to be the x at t plus delta t, but I said let's call delta t h. So x at t plus h minus x at t divided by h. Again, I'm replacing delta t with h. So this is going to be an approximation for what? For the derivative, right? And now this guy is equal to f of x and t. And when I say x, means x at the current time point and current t. And now that I got this one, all I need to do is to cross multiply both sides by h and then take x to the other side. So you will get x new is equal to current x, or x old, plus h times the forcing function evaluated at the old x, or you might call it current x and future x. And this update equation that you see here is just the same as what I showed you over there. Okay, that's called the Euler method. Clearly this method is going to work, and it's going to be good when, as you saw, this h or delta t is a small number. Okay, otherwise it's not going to give you accurate results, and I'll show you with MATLAB code soon. But this is an update equation. Okay, we call it a recursive or update equation. And now, since it was a first order ODE, you need also one initial condition, and the initial condition is, let's say, x at t of 0 is something. Okay, let's say it's, for example, you just come up with a number, let's say 2. Okay, so now, and as I said, I choose h to be what? 1 over 1,000. So I have the x at the beginning. Now, if I plug into this equation t of 0 and h of 0.001, what happens? It means if I add my initial x and add this term to it, which is the step size times the forcing function evaluated at the initial point, it will give me the value of x at which time point? At 0.001. So for example, if I continue with this, you will see that x at time 0.001 is going to be initial x, which is 2, plus 1,000 times the value of this forcing function evaluated at what? At t of 0, and x at time t of 0, which was what? 2, the initial condition. So if you do it here, you're going to get 8 plus 5, that's 13. This is 0, so 13 minus cosine of 4. And 4 here is 4 radians, of course. So you see, now I can have what? X at time 0.001 evaluated. So my next point is generated. Now I come back to this equation, and now I say, well, now I have x at what? I have x at t of 001. And this is whatever it is. Let's say now is, for example, 3. And now I go back. Let me actually calculate the exact number instead of just coming up with a bunch of guesses. So it is 0.001 times 13 minus cosine of 4, which is 0.0137. So this number is 2.0137. Okay, so now this is the new x, and now wherever I see t, now instead of 0, I plug in what? I plug in the new time points that I have. Okay, right? And so now it will give you x at what? 2/1000. So if you do it now, it will be what? X at 2000 is going to be x at 1000, which is this number, plus again this time step or step size, the value of the function evaluated at those numbers, right? So now instead of 2, I have to put 2.0137, 2.0137. This t is now 0.001, and this. So now I evaluate this number, and it goes right here, and it gives me what? X at 0.002, and then I keep repeating this, go to 0.003, and keep going until t reaches what? The final time that I want for the simulation. And that gives me a bunch of points. So clearly you see how this recursive update equation is working, right? And now first let me show you a demo, and then we come back and discuss more. So here is a MATLAB function that I wrote for it, Euler demo. Here you pass to it the handle of the function, which is the right hand side of the Euler, correct? The forcing function. You pass to it the initial condition, you pass to it the initial time, you pass to it the final time, and you also pass to it the time increment dt, which for us is the same as h. So if you like, I can change it to what? H, right? So wherever I have dt, I can plug it with what? With h, and that will be the same thing. So this is what this method does: initial time, step size, final time, initial condition, and the forcing function. And it solves the first order ODE for you by a while loop, keeps increasing t until you reach the t final. It basically evaluates the forcing function at the current t and x, add the previous x, get the new x, and keep saving them, and finally giving you what? A solution. So here, if I want to show you, here is an ODE like this, and my initial time is 0, my final time is 5, my initial condition is 2, my time increment is 0.025. Now let me first make this small, like what I said, 0.001. And my forcing function is this nonlinear function here, which is negative 0.1 x cubed plus exponential negative x plus sine x squared plus cosine of t divided by 5. So clearly time dependent. I define it as an inline function using @ sign and t and x. And then I pass that function with everything else to this function called Euler demo. It gives me the t values and the x values, and then I can what? I can do a plot. So here we go. I'm going to run this part. I did. And now I'm going to do a plot of the Euler solution, which is here. There we go. So these are the solutions. Okay, clearly you have tons of data because you went from 0 to 5 with increment of 0.001. So your solution is now going to have 5,001 data points. So you have 5,001 small triangles, which are all connected by a line. If you want, you can zoom in and you can see that. Okay. Right. So you clearly can see the solution is made of a bunch of points that are connected by lines, and the behavior of the solution looks something like this. Okay, here I'm using a what? A small sample size. Yes? Now, I want to repeat this and keep this plot. On the top of this, I want to replot it, but this time for everything else the same, the only thing I'm going to change is this step size. So instead of 0.001, I'm going to make it 0.1. And I say, well, maybe I do not need 5,000 points. Let's just use 50 points, 51 points. So what I will do is this. First, I go back here and I clean up some of the stuff that I needed, and one of them is T of the Euler and the other one is X solution of the Euler, okay, because I want to rewrite them with smaller vectors. So I clean the big vectors and replace them with smaller vectors one more time. Okay, so here dt is changed. These other stuff are the same. I run the Euler demo one more time. Okay, you clearly see the number of points is changed. And now I will do a plot on the top of previous one with the hold on, and this time I'm gonna make it red triangles instead of blue triangles. Okay, yes, hold on, of course, with the space. And now I will see them on the top of each other. Clearly, as you can see, the new plot has a lot less data points, and the two plots are not exactly the same, especially in this area. Okay, you see some drift, some deviation. Now, which one is closer to the actual solution? We don't know because we don't know the actual solution. But clearly you see that when the step size is changing, you see some drift between different solutions. Now I keep this, I redo it again. This time I clean this up again, and this time I make dt even bigger. I make it like 0.5. Okay, you might say, well, maybe 10, 11, 12 points is all I need. Well, let's find out. I call my function again. And then I say, hold on, and this time I use maybe a black color, okay, on the top of the previous one. And now take a look. Boom. Now you clearly see that the solution is what? Diverging. You do not see any nice behavior. So there was somewhere between 0.1 and 0.5 where this numerical solution is clearly what? Going off track, right? So clearly you can see the behavior. Now this 0.5 is completely meaningless. So you cannot just arbitrarily get h bigger and bigger, and one of the things you have to do is called convergence analysis. So you have to basically start with some h and then start making it smaller, maybe each time by a factor of 2, until what? Until when you make it smaller and smaller, you don't see any change in what? In the outcome. Then you might say, well, I think my h is small enough. Okay, and that's one of the things you might have asked. Well, how do I know the h I have chosen is small enough? Okay, that's what you need to do. You start with some h, in this case, maybe even 0.5. That's fine. You run it with 0.5. You clearly see this meaningless plot. And then you chop it in half, make it 0.25. You see some dramatic change. You make it 0.1. You see another big dramatic change. Make it 0.05, 0.02. And after some number, you might not see a huge difference. Okay. So just for the sake of learning, I run it with a couple of other numbers. So for example, I run it with 0.2 and I plot it on the top of the previous one. This one may be green. Okay, So now you see the green is closer to these other ones compared to black. So green is way, way better. Green is converging to the underlying function, but black is completely off. Okay, so 0.5 is out of question. We are not going to use that. 0.2, we are getting better. 0.1 is still better, but I see a big difference between 0.1 and 0.2. So I'm not going to stop at 0.1. I need to go down further. And as I said, let me run it with something smaller than 0.1, but not as small as 0.0001. So maybe I run it with something like 0.025, okay? And run it again, and then plot on the top of the previous one something with a new color. Now I need, so I have that, maybe C for cyan. And now if you look and zoom in this area where all the differences are happening, you see now the gaps between these solutions is getting smaller and smaller. So clearly when you go from 0.1 to 0.025, you still see some dramatic change, depending on, by dramatic it depends on your application. So now you're getting there. So maybe even 0.001 is not needed, okay? Maybe you can just go to 0.01, right? Let me do one final one. This time just make it 0.01 and run it one more time and do one more hold on, and here we do another color. And well, what colors do we have? Red, black, green, blue. I guess I used them all. And what I can do is I can change my color with RGB values. So I say color and then provide an RGB value. Let's say I go with 1, 1, and 0, red and green, right? Or if you want, you can make it red and blue to make it violet, red and green, correct? Or blue and green, or anything. So this is red, this is green, and this is blue, or I might make them 0.5, correct? You can find RGB of anything that you want on the internet from RGB values. If you want gray, for example, you can use all of them to be 0.5. And here we go. So now the gray is 0.001, and clearly if I zoom in, you see the gray is almost the same as what? The blue. Some changes. It's not exactly there, but you might well say, well, the difference between this gray and blue is not significant, meaningful. So instead of 0.01, I go 0.001, I go with just 0.01. 10 times less data, faster solution, and a lot less data to deal with. So it depends on the accuracy of our application, whether you want to do interpolation later on or not, that you will choose your step size, okay? So anyways, you can see here the effect of step size that we talked about. I mentioned the forcing function and everything, and now let me talk about the Runge-Kutta fourth order, and then we'll talk later about what about higher order ODEs. So as you saw, this Euler method is relatively nice. It gives you a solution, and the accuracy of the solution depends on how small of h you are choosing. The bigger the h, the bigger the chance that you are getting off from the actual solution. Now in this example I solved, I could not solve analytically for the ODE, so I could not see the actual underlying solution because I didn't know what it is. But to just give you a comparison here, I change my right hand side to a forcing function for which I know the analytic solution. And now I will plot what? The analytic solution on the top of the numerical, or numerical on the top of what? The analytic solution, okay? And here, I'm not going to do Runge-Kutta for a moment. Okay, so here, my right-hand side is simply negative x. Okay, so I easily know the analytic solution for it. So this time, your ODE is x dot equals negative x, and clearly, since this is dx over dt, I do separation of variables, so you will get dx over x is equal to negative dt by a cross multiplication, and then you integrate it. This goes from 0 to t, this goes from x naught to x. And clearly this is natural log, so it is going to be natural log of x minus natural log of x naught, and this is negative t. And here you can combine them, make it natural log of x over x naught equals negative t. Now you raise both sides with exponential, so it will be x over x naught is e to the negative t. And now your solution x of t is going to be x naught times exponential negative t. So I have my exponential solution here because it's so simple. And that's what I did in this code. I have the solution, exact solution, okay, which you can see here. And I'm going to plot it. And on the top of that, I'm going to plot the solution to the from the Euler method with 0.01, or if you want 0.25 first. And you can see the difference between exact and numerical. So the black is exact. These points are what? Numerical. You see clearly there is a difference. Now, if I make this 10 times smaller, you see the difference should be way less visible, right? So it's barely visible. They're kind of overlapping. Very, very close. And if you made this, of course, even 10 times more, 10 times smaller, now you probably have kind of like a perfect overlap. Okay, you see, you're almost there. Small, small, small differences. It's a very, very small number. You see, in the fourth decimal is what they are different. And you can go smaller and smaller, but you get more and more points. It takes more time to solve. And at some point, it does not really worth it for your application to just keep shrinking this down. Okay, so clearly you see here the Euler method and the step size and everything. Now, as you just saw, when this number is big, like this, the solution, numerical solution, is quite different from the exact solution. And we have to reduce it. Now, one of the other ways to handle it, instead of just bringing this h down and the number of points up, is can we change our update equation and the way we approximate the derivative such that the solution we get for the same amount of h is closer to the actual solution compared to the Euler method? And the answer is yes. And that's where these other algorithms of solving ODEs numerically come into place, like the Runge-Kutta fourth order. So if you look at the Euler method, the error between the actual solution and the numerical solution in general is proportional to h. Okay, is proportional to h. So for example, if my h is 0.1, then the amount of error due to this truncation, or approximating the derivative basically, it's proportional to point what? To 0.1, right? So with h of 0.1, I have a difference between the actual and the numerical, something similar to 0.1 or proportional to that. 2 times that, 5 times that, 6 times that, 1.5 times that, something like that. But the Runge-Kutta fourth order which we'll talk about the update equation of it in a second, the error of this method for the same h is proportional to h to the 4. Okay? So the error of the Euler, if h is 0.1 that we are using, the error for the Euler is what? Proportional to 0.1, while the error for the Runge-Kutta fourth order is proportional to 0.1 to the 4, which is what? Point, of course, 0, 0, 0, what? This is 10 to the negative 4, which is this guy, correct? This is 10 to the negative 1 to the 4, that's 10 to the negative 4, 1 over 10,000. And clearly this is way more accurate than that. So Runge-Kutta for the same h is about what? 1,000 times more accurate, or it has 1,000 times a smaller error compared to the Euler method. And that is a big thing because we have not changed h, we have not changed the number of data points. But it comes at a price. What price? Instead of this simple update equation that you only do one time, now your update equation is something like this. Y at the next, or x at the next, depending on how you define your dependent and independent function. The dependent function at the next iteration is whatever it was at the current iteration plus 1/6 of 4 numbers added together, k1, 2k2, 2k3, and k4, where this k1 to k4, they are coming from the forcing function. The first one is the forcing function evaluated at the current what? At the current point times h. So this part of it is very similar to the Euler. Then when you get k1, you add half of that to the current y, you add half of a step size to the current x, and re-evaluate the forcing function multiplied by a step size, that's k2. Then k2 is used here for k3, and k3 is used here for what? k4. And once you get all k3, k1 to k4, you plug them into the update equation. So instead of a simple step update equation for y, now your update equation for y involves 4 steps here for k's and then 1 step here for the y itself. So you have 5 steps for updating what? Y values. The x update is still 1 step, but y values, the update is 5 steps instead of 1 for the Euler. But it gives you what? You can use smaller h, and it gives you a lot what? A lot more accurate solution. Now you might say, well, which one worth it? Here I need to get, let's say, from both methods to get to the same accuracy. Which one is better? Because here you only need to do this computation once, one update equation, and it doesn't have a ton of calculations in it, so it allows you to choose what? A smaller h and get more and more points. While in Runge-Kutta, since you are doing 5 calculations instead of 1, if you use h as small as Euler method, now for this method you are doing a ton more calculations. And so the Runge-Kutta is going to be slower. So if you want to keep the speed and accuracy the same, which one worth it? And it turns out, although this here uses 5 updates instead of 1, but because of this huge difference, h to the 1 to h to the 4, still Runge-Kutta fourth order worth it over the Euler method. Still, for the same speed, this method can be more accurate. And here, just to show you, if I use the same h, for each one of these methods, and I'm going to use that big forcing function instead of the actual one for a moment, or well, let's use the actual one because I know the exact solution, so I can have an idea of which one is closer to the actual one. So here I solved this simple ODE analytically using Euler and using Runge-Kutta, the function for which I have written here. And clearly see it involves calculating K1 to K4 and then using them to update my dependent function. And it takes similarly all of the stuff that Euler did. And I put all of them on the same plot, okay? For both of these methods, I'm using a big H. So let's take a look here. So here I'm using a big H. So clearly you see Euler solution, the blue triangles, is quite what? Off from the actual solution. But look, for Runge-Kutta, although the H was big, 0.25, but look, it's what? It's on the top of the exact solution. Here you see the difference, right? Runge-Kutta can basically work with what? With a big H, and yet give you almost perfectly accurate solutions. Okay, that's the advantage of the Runge-Kutta. It's accurate. And so now you might say, well, can't you use a smaller thing for H? Sure, I can. But how far should I make H for Euler smaller until I see this perfect overlap, right? So clearly here you see Runge-Kutta with 0.25, it was good. Euler, if you remember, at 0.5, it was completely what? Off track. It completely diverged. Now, if we make 0.5 for Runge-Kutta, what happens? Look here. Right? Now, this is because, in this case, it doesn't diverge, of course, because I changed my forcing function. The last time it diverged was because the forcing function was that big forcing function, not simply negative x. But clearly you see the gap is getting bigger and bigger between Euler and actual, while Runge-Kutta is still holding on, still hanging there, right? Perfectly similar to the actual solution. Now let's try it with this one. The difference is this time I do not have the underlying function, but I can see the difference in behavior. So here there is no exact solution, so I should turn this exact solution off, because there is no exact solution here. There we go. As you can see, Runge-Kutta is still holding on and hanging there perfectly, showing some solution that is not clearly diverging, but Euler is completely off. Now I bring it down, make it 0.1, and you see that while Runge-Kutta changed a little bit, Euler changed dramatically. Okay, so if I wanted to, I could easily run these two guys for different dt's and solve for it. So let's do that actually. For Euler, I'm going to use 0.01. For Runge-Kutta, I'm going to use 0.1 or 0.05, right? Which gives me 5 times less data. So this is what I will do. I make the dt for Runge-Kutta 5 times bigger to kind of compensate for 5 update equations instead of 1. Run them and look at it. Here. You see, they're almost on the top of each other. And actually Euler is converging to the Runge-Kutta. So it means Runge-Kutta is more accurate. But clearly you see that even using a bigger h for Runge-Kutta still is a little bit more accurate than a small number for Euler, while the calculations are the same. Okay, so clearly you see that why in the literature this Runge-Kutta is preferred over Euler method. It's like more advanced. So these are some of the demos I gave you. Now let's go to the last topic that I mentioned for today's video, and that is what happens if you want to solve higher order ODEs with these guys. What should you do? And for that, I'm gonna go back to my ODE that I started my lecture with. Theta double dot equal negative G over L times sine theta. Okay, and with two initial conditions, theta at 0 is, let's say, pi over 3, and theta dot at 0 is 0. And let me call theta dot omega. So omega at 0 is 0. Okay, since we only can solve first order ODEs with Euler, and this is second order, we have to break this second order into two first order ODEs and then try to solve both of those first order ODEs at the same time. Most of the time they are coupled and you have to solve them simultaneously. So to do that, we use some dummy variables. In controls, we call them state space variables. And in this case, the dummy variable, how many of them do I need? As many as the order of the ODE. Second order, so I need 2 of them. And they can be chosen as the dependent function and its time derivatives most of the time, or any combination of them. There is no unique solution to this part, but one of the most common ways to choose those variables is I choose the first variable to be theta, and the second variable I choose it to be theta dot or omega. So again, 2 dummy variables, I call them Z1 and Z2, and I chose them to be theta and theta dot. And now using these 2 variables, I will convert the second order ODE into 2 first orders. How? Let's take a look. So the first thing I need, I take a time derivative out of these 2, and it will make my Z1 dot to be equal to theta dot, but theta dot itself is what? Z2, correct? And then Z2 dot is going to be theta double dot, and theta double dot from my governing ODE here, it is negative G over L sine theta. But theta is Z1, so it's going to be negative G over L sine of Z1. So now you clearly can see my 2 first ODEs, first order ODEs. One of them is Z1 dot equal Z2. The other one is Z2 dot equal negative G over L sine Z1. Clearly you have to solve them at the same time, because for this equation to solve, you need Z2. For this equation to solve, you need Z1. So you have to simultaneously solve the system of ODEs, but both of them are first order, as you can see. And you can also write your initial conditions in terms of these ODEs. So if I want to rewrite everything, it is going to be Z1 dot equals Z2, and then Z2 dot equals negative G over L sine of Z1. And your initial conditions are, so it is subjected to that Z1 at 0, remember Z1 is theta, is pi over 3, and Z2 at 0, which is omega, it's what? 0. So clearly, you're now solving 2 first order ODEs. And now, I have 2 forcing functions. So this one, I call it forcing function 1 of Z1 and Z2, and in general, T. Now, there is no T here, but in general, it could be. And this guy here, I call it what? The second forcing function, F2 of Z1 and Z2 and T, okay? So now if I use vector notations, so if I introduce vector Z, which is Z1 and Z2, and if I introduce vector F, which is F1 and F2, By the way, this is Z1 of t and this is Z2 of t. Then my Euler method, let's say my Euler's method for this system of ODEs, the update equation is going to be, so this is Z at time t, correct? It's going to be vector Z at time t plus h equals vector Z at time t plus h times the forcing function evaluated at Z at t and t, right? Because this whole thing can be called what? Vector Z. Okay? So this is my update equation. So now at any time points, starting with initial conditions of Z, I plug them into the forcing functions, which are these two guys here, evaluate them, then multiply them by h, add them to initial z's, and I get what? Z at t plus h. So for example, for this case, if I say h is, let's say 0.1 and t initial is 0, this means Z at time point 1, which is basically theta at time point 1 and omega at time point 1, is equal to whatever they were at time 0 plus h, which is 0.1, times the forcing functions evaluated at time 0. So this is going to be Z2, which is omega at time 0, and this is negative g over L sine of theta at time 0. Yes? So you see, having the initial conditions, these two numbers that I have, and plugging them here, and with the time step, I can calculate my theta and omega at the new time point and then keep repeating it and get theta at the new, and finally I can plot what? If I want, I can plot theta versus t, and I can also plot what? Theta dot or omega versus t, okay? And this is what the function ODE45 in MATLAB is doing, okay? ODE45 in MATLAB, you can solve with it a system of first order ODEs, whether linear or not, it doesn't care, with some initial conditions, and it returns to you all of the dummy variables evaluated at all time points, and then you can plot them. So for the last thing I want to do, I show you how to solve this nonlinear pendulum using MATLAB command OD45. Now, the command OD45 in MATLAB is not going to use Euler method. It is going to use Runge-Kutta method, okay? So it does all of those 5 steps of updates with these forcing functions, not just one step, okay? It uses more accurate solver instead of Euler. But the idea is the same. So what I will do here is to just show you how it is done. I will define a function, and this function will be used by ODE45. If you don't know how to use it here, you can just say ODE45, which is one of the different methods in MATLAB for solving differential equations. What type? It's called non-stiff. What is non-stiff? It's the topic for a separate video. But here you can just assume that like the forcing functions are smooth and nice behaving functions. And the initial conditions also, and the boundary conditions are also regular normal conditions. So I'm not going to get into discussion of stiff right now and non-stiff conditions. But you can see how this function is called. You have to pass through the function, the time span, and initial conditions, and it gives you back the time points used in solve and the vector of all dummy variables, okay? So if you want to know more about ODE solvers, you can go here, and there are different types of ODEs that MATLAB explains for you. If you want to solve a system of ODEs, higher order ODEs, here it explains. You can see here MATLAB is explaining to you how to use these dummy variables. You can see that here. Complex ODEs and so on. And then these are different ODE solvers in MATLAB, 4523, 1523S, and so on and so forth. Each one of them is for a specific application. Okay, so if you want to know more, go and take a look at that. But what you need is, as I said, there is a function that you need to have. This function will give you the right-hand side of those governing ODEs. Basically, what it does is, if I go back here, it basically incorporates these two equations for you. This is what this function does. The output of it is vector z dot. The input of it is vector z and time t, and it describes these two forcing functions f1 and f2. Okay, so let me show you how you should do it. So here I say z dot equals, let's say, non-linear pendulum of t and z. And z dot are both vectors. And then I say z dot number 1, okay, which is the first equation, basically. It is what? It is z number 2, and z dot number 2 is negative g over L sine of z number 1. So this is z number 2, and then z dot number 2 is negative g over L sine of z number 1. And here, this function needs to know g and L, so you have to describe it for him. G is 9.81, let's say, and L is, let's say, I have 30 centimeter or 0.3 meters length of the pendulum, and these are the governing equations. That's all it is, and I save it with the same name as the function, NPL. And now, in a script, I provide some initial conditions. So my initial conditions, z naught is equal to the first parameter, which is theta. The initial condition for it is pi over 3, and then for omega it is 0. The time span is equal to, I want to solve it over 10 seconds, so 0 to 10. And now I say the solution t and the solution z is equal to ODE 45 at sine. Here you provide the name of the function, NPL, and then you pass to it what? The t span and the initial condition. Okay, as you can see here, that you pass t span and initial condition. That's the syntax for this command, right? And finally, once you get it, you can plot the time points versus what? Versus the first column in Z. As you remember, Z is what? Z has Z1 and Z2, or theta and omega. The first parameter is theta, the second one is omega. Now, this Z solution is a matrix, actually. This Z solution is a matrix. And the first column of that is Z1, which is theta. The second column of that is Z2, or omega. And it has a bunch of numbers in it. Each number is for what? For a different t value, right? So this is t naught, this is t naught plus h, all the way to t final, right? And this whole thing, we call it vector t. So the first column of Z is theta that you cared about, the solution. So now you say plot t and what? Column 1, right? So let's do it. So I call it test and run it. Now if it gives you error, don't panic, always take a look. So it says unrecognized function or variable npn. So you have to first make sure this npl that you wrote is available here, and it is. I call it NLP, not NPL. You see, small thing is enough to throw it away. So NLP, nonlinear pendulum. Now what? You still got an error. What is that? Says it must return a column vector. This is a common error that you would get when you run this. And to do that, all you need is you come here and say this z dot is equal to zeros of 2 and 1. Initialize it or pre-allocate it as a column vector and then run it. Okay, so now let's see. There we go. Okay, so this is your solution, and to show that it's coming from a bunch of points, I will use blue circles here for you. So now you can see it better. Okay, so they come from the solution. Now the solution might look like a perfect harmonic function. It is not. The amplitude of these oscillations does change a little bit, and it's called quasi-periodic. But again, discussion of that will get us into nonlinear dynamics, and I don't want to get there. But there is no function to describe these oscillations with the amplitude variable with respect to time. So although it might look like a simple sine or cosine function, it is not. It's a little bit more complicated. And actually, there is no mathematical function to describe these nice-looking oscillations. Okay, so this is theta versus time. But it does oscillate. Okay, it does oscillate. Now, not as simple as a sine function. So anyways, that's the solution for any higher order ODE. Just use enough of dummy variables, break it down, the nth order ODE, break it down into n first order ODEs, and then solve all of them simultaneously. Okay, so you can either write your own code, so modify basically this Euler code I wrote, or RK4, or you can directly use the built-in function in MATLAB, which uses Runge-Kutta or other solvers. It's called OD45. And you just form your functions and let this take care of the update equations and everything. So hopefully I could provide you with some good knowledge about how to solve differential equations numerically using two methods that are well known and then the built-in function in MATLAB. I will see you in the next lecture. Thank you.